The EPD framework, a novel planning architecture, addresses the egocentric task planning problem in the EgoPlan Challenge at ICML 2024. This three-stage framework consists of long-term memory extraction, context-aware planning, and multi-iteration decision-making. By leveraging the strengths of multimodal large language models, MLLMs, and video models, EPD effectively tackles real-world egocentric task planning. A key innovation of EPD lies in its template-based approach to prompt MLLMs, focusing on task goals, real-time progress, and current observations. This method significantly reduces the time and resources required compared to training video models, while still harnessing the extensive knowledge embedded in MLLMs. The EPD framework demonstrates its effectiveness in real-world egocentric task planning, achieving a planning accuracy of 53.85% on the EgoPlan-Test set. This novel approach showcases the potential of leveraging MLLMs in planning frameworks, offering a promising direction for future research in egocentric task planning. The proposed EPD framework addresses the challenges in long-term memory extraction, context-aware planning, and multi-iteration decision-making for complex video-based tasks. It leverages MLLMs to extract key content from video frames, plan actions based on current observations and memory, and selects the most reasonable plan through multi-iteration decision. The framework is training-free, achieving a planning accuracy of 53.85% on the EgoPlan-Test set, a 10% improvement over the baseline. The methodology involves extracting memory text information from video segments using the GPT-4o model, planning the next action with the memory text and current observation, and employing multi-iteration decision to select the best plan. This approach significantly surpasses existing baselines, demonstrating its effectiveness in complex video-based tasks. The authors propose EPD, a novel solution for the EgoPlan Challenge at ICML 2024, comprising long-term memory extraction, context-aware planning, and multi-iteration decision-making. The task involves predicting the next action of an agent in an egocentric video based on the current observation and task goal. EPD leverages GPT-4o, a multimodal large language model, for memory text information extraction and planning, resulting in a 4.3% performance improvement compared to Lavila. By prompting GPT-4o to describe the visual content of the input image, the authors enhance the model's understanding, achieving a 3.79% performance improvement. The authors explore the multi-iteration decision phase, initially using a simple option counting method, which selects the most frequently occurring option from 5 results, resulting in a 0.88% performance improvement. They further refine the decision approach by using GPT-4o to decide whether GPT-4o's planning or Claude 3.5's planning is more convincing, achieving a 1.14% performance improvement. An ablation study examines the impact of different planning models and the inclusion of video input on the results, revealing that GPT-4o exhibits stronger multimodal planning capabilities on EgoPlan compared to Claude 3.5. However, training-free models are limited in their ability to achieve fine-grained egocentric visual understanding capabilities. A case analysis highlights the limitations of GPT-4o, which still lacks fine-grained visual understanding, often incorrectly interpreting actions in certain scenarios, such as mistaking pick up knife for pick up broccoli. Figure 1 illustrates the framework of EPD, and Table 1 presents a performance comparison of different models on EgoPlan Val-OD and EgoPlan-Test. The table on solution evolution, Table 2, showcases the incremental improvements in order accuracy achieved by the EPD framework through various modifications. Starting with an initial accuracy of 41.28%, the model is fine-tuned to extract long-term memory, resulting in an accuracy of 45.58%. Subsequent modifications include adopting 4-shot in-context learning, utilizing high-resolution observations and output descriptions, and incorporating multi-iteration decision-making with GPT-4o and CLAUDE 3.5 results, ultimately achieving an accuracy of 53.85%. An ablation study, presented in Table 3, investigates the impact of different planning models and input information on accuracy. The study reveals that incorporating memory information into the input video enhances accuracy, with GPT-4o achieving an accuracy of 51.83% when combined with memory information. The extraction prompt provided in the text is used to elicit the sub-goal of a given video, which is then compared to the overall goal. For instance, in the example shown, the sub-goal is to pick up the broccoli, given the overall goal of add garlic to the food and stir. However, Figure 2 illustrates a wrong extraction with GPT-4o, highlighting the limitations of training free models in capturing fine-grained visual semantics. The authors emphasize the significance of the EgoPlan task in practical terms, noting that trainable models have substantial potential for improvement. The proposed EPD framework demonstrates its effectiveness in achieving a planning accuracy of 53.85% in the EgoPlan challenge, while also identifying the limitations of training free models. In the realm of video understanding, language models and video representations have emerged as crucial components. The authors draw upon relevant works, including Xiang et al.'s Video LLAMA, an instruction-tuned audiovisual language model that demonstrates the potential of combining language models with video data. Zhao et al.'s approach to learning video representations from large language models is also acknowledged, highlighting the importance of leveraging language models for video understanding tasks. These cited works underscore the significance of developing models that can effectively process and analyze video data, a crucial aspect of the EgoPlan challenge. The author's EPD approach, comprising long-term memory extraction, context-aware planning, and multi-iteration decision-making, is positioned as a novel solution to tackle the complexities of video understanding. By integrating language models with video data, the authors aim to enable more accurate and efficient video understanding. This approach is built upon the understanding that language models can provide valuable insights into video data, and by combining these models with video representations, a more comprehensive understanding of video content can be developed. The authors' citations of Zhang et al. And Zhao et al. Contextualize their own work within the broader landscape of video understanding research, highlighting the significance of their approach in advancing the state of the art in this field.